everyone, this is Colin from Fiber Optics for Sale. In this video, I will explain what is an OTDR and its applications. OTDR stands for Optical Time Domain Reflectometer. Its name means that OTDR checks the reflected light from the fiber under test along time, shown as the yellow trace line in this picture. The fiber connected to this OTDR is called launch cable. The launch cable is then connected to the fiber under test. I will explain why we need a launch cable a little bit later. An OTDR provides a view of the fiber link by reading the level of light that is reflected back from the fiber under test. There are actually two types of light being reflected back. The first type is a constant low-level reflection created by the fiber called Rayleigh backscattering. Rayleigh backscattering comes from the natural reflection and absorption of impurities inside optical fiber. When hit, some particles redirect the light in different directions, creating both signal attenuation and backscattering. The second type of reflection is called Fresnel reflection. When the light hits an abrupt change in refractive index, for example, from glass to air at a fiber connector interface, a higher amount of light is reflected back, which can be thousands of times bigger than the Rayleigh backscattering. Fresnel reflection can be seen as spikes in OTDR trees. Examples of such reflections are connectors, mechanical splices, bulkheads, fiber bricks, or opened connectors. This illustration shows the construction of OTDR. The pulse generator generates a short electrical pulse, which drives the laser to generate a corresponding light pulse. The light pulse is coupled into the fiber under test. When some light is reflected back from the fiber, it is coupled into a photodiode by the directional coupler. This photodiode converts the light signal into electrical signal, which is then amplified and recorded. This process produces the trace as shown here. The signal sent is a short pulse that carries a certain amount of energy. A clock then precisely calculates the time of flight of the pulse, and time is converted into distance based on the speed of light in this fiber. When the pulse has entirely returned to the detector, another pulse is sent until the acquisition time is complete. So many acquisitions will be performed and averaged in a second to provide a clear picture of the link's components. There are three types of OTDRs on the market now. Laboratory OTDRs are typically used in test labs. They have extremely long range with many options. Mini OTDRs are portable and designed for field testing. They have built-in screens and provide data storage as traces are collected in the field. PC-based OTDRs connect with a personal computer and operate with Windows-based software. They allow saving traces in a disk and then transfer data between computers. Generally, OTDRs are used for testing with the launch cable and may use a receive cable. The launch cable allows the OTDR to settle down after the tested pulse is sent into the fiber and provides a reference connector for the first connector on the cable to determine its loss. A receive cable may be used on the far end to allow measurements of the connector on the end of the cable. Fresnel reflections lead to important OTDR specification known as dead zones. Dead zones are expressed in distance such as meters. A dead zone is defined as the length of time during which the detector is temporarily blinded by a high amount of reflected light until it recovers and can read light again. Think of when you drive a car at night and you cross another car in the opposite direction. Your eyes are blinded for a short period of time. In the OTDR world, time is converted into distance. Therefore, more reflection causes the detector to take more time to recover, resulting in a longer dead zone. The most common place you see this as a problem is caused by the connector on the OTDR itself. The reflection causes an overload, which can take the equivalent of 50 meters to 1 kilometer to fully recover, depending on the OTDR design, wavelength, and the magnitude of the reflection. For this reason, most OTDR manuals suggest using a launch cable, which gives the OTDR time to recover before you start looking at the actual fiber under test. The slope of the fiber trace shows the attenuation coefficient of the fiber and is calibrated in dB per kilometer by the OTDR. Connectors and splices are called events. Both should show a loss, but connectors and mechanical splices will also show a reflective peak. The height of the peak will indicate the amount of reflections at the event, unless it is so large that it saturates the OTDR receiver. Then peak will have a flat top and a tail on the far end, indicating the receiver was overloaded. Reflective pulses can show you the resolution of the OTDR. You cannot see two events closer than is allowed by the path width. Generally, longer path widths are used to be able to see farther along the cable plant, and narrower paths are used when high resolution is needed, although it limits the distance that OTDR can see. The next thing you must understand is OTDR resolution. The OTDR test path has a length in the fiber, typically 5 to 500 meters long. It cannot see features in the cable plant closer together than that. If the light pulse is too long, the pulse will be going through both events simultaneously, and OTDR cannot distinguish these two events as shown in the picture. This has been a problem with LANs or any cable plants with patch cables, as they disappear into OTDR resolution. If the pulse is too short, it loses its energy before the fiber end, causing the backscattering level to become low to the point where the information is lost at the noise floor level. This results in inability to reach the end of the fiber. When the OTDR sends a test pulse down the cable, the big reflection from the far end comes back to the OTDR, where it shows up on the trace as an overloaded reflection. Then is reflected from the OTDR interface back down to the cable for a second trip, effectively becoming a second test pulse, which is reflected back from the far end yet again, going back to the OTDR to be recorded as a second trace. If the reflections are big enough, this process can go on 3 or 4 times, each time producing a ghost event on the OTDR trace. There are 5 important parameters you need to set in OTDR: fiber type and wavelength. Choose the wavelength that you wish to use to test the fiber. Refractive index is used by the OTDR to calculate distance from measured time based on the speed of light in this fiber. Distance range. In an OTDR trace, the distance range should be at least twice the value of the cable's total length. Pulse width is the length of the light pulse that is initiated by the OTDR to travel through cables and create a trace. Longer pulse widths are effective for testing long distances, while shorter pulse widths provide higher resolution. Number of averages is the number of repetitions that OTDR will send the pulse before calculating data and creating the trace. A good place to start is 64 averages, which will give good range and fast trace acquisition. So there you have it. Please don't forget to visit foforsale.com for more free fiber optic tutorials. I will see you in the next video.